nucleophilic substitution reactions. Okay, so how to prepare? How alkyl halides undergo nucleophilic substitution reactions. Okay, so we have seen different substitution reactions, right? So based on that also we have solved some MCQs. Okay, then we had started with elimination reaction. So elimination reaction, where so it follows, so whenever there is a alkyl halides, okay, so alkyl halides, they undergo beta elimination reaction in the presence of alcoholic KOH to yields alkene. Okay, so whenever you have an unsymmetrical alkyl halide, suppose you have a unsymmetrical alkyl halides, so that time the elimination will follow which rule? It will follow Setzef rule, right? So according to this, what will happen? The hydrogen will be eliminated from the carbon atom, which has less number of hydrogen atom, and thus highly substituted alkene will be the major product which is formed. So this is the elimination reaction. Okay, so we have seen this also. Then based on that, so what is the order of reactivity of alkyl halides towards dehydrohalogenation? What do you mean by dehydrohalogenation? We have discussed. So there will be removal of one hydrogen and one halogen atom. Okay, one hydrogen and halogen atom will be removed, eliminated. So it is called as dehydrohalogenation. So we had discussed which is the dehydrohalogenating agent. It is alcoholic KOH. So this question is commonly asked, which is the dehydrohalogenating agent, that is alcoholic KOH. Okay, so we have seen this examples also. So we have solved this MCQs. Okay, so we have to start it from here. So what is the reactivity order of alkyl halides for dehydrohalogenation is? So these are the four options. So which is the order of alkyl halides for dehydrohalogenating? Yes. So when you are seeing the reactivity order of alkyl halides, so these are all halogen atoms. You know fluorine. So you know the arrangement, okay, in the column, how it will be: fluorine, then chlorine, then bromine, and then iodine. So as you go down the group, what will happen to the size? Size will go on increasing, right? The size of the halogen atoms, it goes on increasing, right? So what will happen as you go down? So negative charge is on larger atom. So you know that as you go down, what will happen? The negative charge which is there, it will be more on the larger atom. So the carbon halide bond, it breaks more easily. So if the negative charge, it is said that negative charge will be more when you have a larger atom. So you know that as you go down the group, so fluorine is the smallest atom and iodine is the largest. Okay, so the carbon iodide bond, it will break easily, more easily than the CF bond. So which is answer? Our answer is B. Okay, so the order of reactivity of alkyl halides for dehydrohalogenation is Ri. Okay, Ri is greater than Rbr, is greater than RCl, is greater than Rf. Okay, so it will be smallest. The reactivity order will be smallest for fluorine and it will be largest for the iodine. So B is the answer. So next we'll see the reaction with metals. Okay, so when alkyl halides, if they react with metal like sodium, okay, if alkyl halides, if they react with metals like sodium, okay, so in the presence of a dry ether, the solvent uses ether, okay, it will be dry. Okay, so when you use, so your 2 moles of alkyl halides are treated with sodium in the presence of sodium in the presence of dry ether, it yields alkane. Okay, it yields what? It yields alkane plus sodium halide. It yields what? Alkane plus sodium halide. Okay, so this is the reaction, very important reaction, and this named reaction is called as Wurtz reaction. it is called as what? Wurtz reaction. So for Wurtz reaction is used for preparation of alkanes. Okay. So here, what is our starting reactant? We are taking alkyl halides. Okay, we are taking 2 molecules of alkyl halides. We are reacting it with metal like sodium. Okay, in the presence of dry ether, giving you alkane plus 2 sodium halide. So this is the reaction. Then second reaction is we are going to react our alkyl halide with magnesium. Okay, when you react alkyl halide with magnesium in the presence of dry ether, again the solvent uses dry ether, we get the product called as Grignard reagent. What is Grignard reagent? RMGX. Okay, so Grignard reagent is also called as organometallic compound. Why it is called as organometallic compound? There is a presence of organic. Okay, carbon. Carbon is what? Carbon means it is a organic compounds, right? Carbon compounds are called as organic compound. So R, alkyl group is nothing but it is a carbon compound. So Mg is what? It is a metal. So it is organometallic compound. So when alkyl halide, when it reacts with magnesium in the presence of ether, it gives you RMGX. Okay. It gives you what? It gives you RMGX. That is Grignard reagent. Okay. It is called a Grignard reagent. Next we are going to react our alkyl halide with metal like lithium. So when you treat alkyl halide with 2 lithium, it gives you RLi. Okay, plus LiX. That is alkyl lithium is formed. It forms what? It forms alkyl lithium. So when alkyl halide is reacted with lithium, it gives you alkyl lithium. Okay. Next reaction is Wurtz-Fittig reaction. What is Wurtz-Fittig reaction? Okay. So we have seen what is Wurtz reaction. In Wurtz reaction, we have taken what? We have taken alkyl halide. Now in Wurtz-Fittig reaction, we are going to take 1 molecule of alkyl halide and 1 molecule of aryl halide. Now we are familiar with the words what is alkyl halide, what is aryl halide. Okay. So aryl halide is what? It is an aromatic compound. So we are going to treat what? We are going to treat alkyl halide. Okay, and we are going to treat with sodium metal and 1 aryl halide in the presence of solvent like dry ether, and you get what? You get toluene. So how is this reaction? I'll just show you. I'll show you with structures. So this is CH3Cl plus 2Na plus C6H5Cl. Okay, they have written the formula. It can be written as this. So in the presence of dry ether, it gives you what? CH3. Okay, it gives you like this. So this is the product what is formed. So this, the name of this compound is toluene. So this is 2Na, 2Na and Cl will combine, and this will combine. Okay, and this will also combine. So 2NaCl is product, and this will combine with this. Right. So this is the reaction. It is called as what? It is called as Wurtz-Fittig reaction. It is called as what? It is called as Wurtz-Fittig reaction. So based on this, we'll solve some MCQs. CH3MgBr is an organometallic compound due to. So why it is called as organometallic compound? Due to what? A, MgBr bond, C, CMg bond, that is carbon Mg bond. Then third option, CBr bond, and the fourth option is CH bond. Yes. Why it is called as organometallic bond? Due to what type of bond which is present? Okay. Aishwarya has answered it as C. What about others? So CH3-MgBr, just now I discussed CH3-MgBr is called as organometallic compound because you have a organic carbon compounds are called as organic compounds. Then you have a metal in that. So it is called as organometallic compound. Why it is called as organometallic compound now? Because of what type of bond which is present? Yes, because of what? Because of carbon and metal. Okay, because of the carbon and Mg bond. So it is what? The answer is B. What is the answer? The answer is B. It is due to what? It is due to carbon and metal bond. Okay, it is due to carbon metal bond. CH, CH, and this is Mg. So it is due to what? Carbon metal bond, right? So CMg bond, it is due to CMg bond. That is CH3-MgBr is organometallic compound due to presence of metal and carbon bond. Why it is called as organometallic compound? Because of presence of carbon and metal bond. Okay, it is due to the presence of carbon and metal bond. It is called as organometallic compound. I hope it is clear. Okay, so we'll go for the next option. Next question. So Grignard reagent is not prepared in aqueous medium, but it is prepared in ether medium. Why? What is the reason? A, it is insoluble in water. B, the reagent is highly reactive in ether. C, the reagent reacts with water. And D, the reagent becomes inactive in water. What is the reason why Grignard reagent is not prepared in water, but it is prepared in ether? Ether is a solvent, right? It is highly evaporated solvent. It will easily evaporate. If you keep the bottle of ether open, the ether will get evaporate. Same like acetone, right? Acetone you use for nail polish, right? The same. So as acetone will evaporate, the same is with ether. Okay, so ether also gets evaporated soon. So Grignard reagent, it is not prepared in water, but it is prepared in ether. Okay, I got one answer as C. What about others? Okay, Sanjay has also answered it as C. And answer C is right. Okay, the reagent, what will happen? Why it is not prepared in water, but it is prepared in ether solution medium? Because the reagent will react with water. Because the reagent, okay, because the reagent may react with water. Because of this, it is prepared in ether. Okay, so I'll show the reaction, how it will react. So if r-MgBr, if it reacts with water, okay, so this is what? This is Grignard. Gives you what? It gives you. So if you treat Grignard reagent with water, it forms alkane. It forms alkanes plus Mg, Br and OH. So it forms what? It forms alkane. Okay. So the reagent reacts with water. Okay, so next question. When 1 chlorobutane and 2 chloropropane are treated with metallic sodium in ether, we get A, 2-methylhexane, B, 1,1-dimethylpentane, C, 5-methylpentane, D, 5-methylhexane. So there are two compounds. That is, one is 1-chloromethane or 1-chlorobutane, and another compound is 2-chloropropane. If you treat it with metallic sodium, okay, that is with ether. So what we get? So we'll write the reaction. So what is the structure of 1-chlorobutane? 1-chlorobutane. So chlorobutane. Butane means 4, right? CH3, CH2, 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 Cl. So this is 1-chlorobutane. Okay, so this is 1-chlorobutane plus 2-chloropropane. Propane means it will be 3. So it will be CH3, CH, CH3. So chloro 2, second position. So this is 1, 2, and 3. So at second position, you have chloro. So this is 2-chloropropane. So when you treat 1-chlorobutane and 2-chloropropane, so both are what? Both are alkyl halides. So when you treat alkyl halides, so these are 2 alkyl halides. So alkyl halide, when you treat it with 2Na in the presence of dry ether. So this is what type of reaction? This is a Wurtz reaction. Okay, so this is a Wurtz reaction. So what type of reaction, what will be the product obtained? What will be the product obtained? Yes, what will be the product obtained? So these are both are alkyl halides, right? When two alkyl halides, when they react with the sodium metal in the presence of dry ether, you obtain a product, that is, you will obtain a alkane. So this name reaction is called as Wurtz reaction. So what will be the product obtained? 2Na, I'll write it here, 2Na plus. Okay. So how it will eliminate? Just see, 2NaCl. Okay. So how will be the product? Product obtained will be CH3, CH2, CH2, CH2. At this CH2 point, this molecule will get joined and this will get joined. Okay, at this point, this will get joined because from here the Cl will be released. So CH2, then will come CH. This is CH3 and this is CH3. Yes, name this compound. Name this compound. This will be 1, 2, 3, 4, 5, and 6. Right, 6 means it will be hexane. Okay, it will be hexane, and at sorry, I have numbered it Wurtà. Here, if I start numbering, so if I number it from here, 1, 2, 3, 4, 5, 6. So this is hexane. So at second position, you have a substituted, that is 2-methyl hexane, right? So which is our answer? Our answer will be A. I hope you have got it. Okay. So it is one alkyl halide. So there is two compounds, that is two alkyl halides are there. One is 1-chlorobutane, another is 2-chloropropane. So when you treat it with sodium in the presence of dry ether, okay, you get what? You get 2-methyl hexane. So I have shown here. So these are the two structures. This is 1-chlorobutane. This is 2-chloropropane. So how the elimination takes place? 2 NaCl. Right. The another substituted product will be 2NaCl. So 2NaCl will get eliminated. Okay. Now here CH3, CH2, CH2, CH2. So at this point, this will get joined. So it will be CH3, CH2, 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 and this will get here. Okay, added here. So it will be CH, CH3, CH3. Okay. So it is 2-methyl hexane. So our option A will be the right answer. I hope you have got it. So we'll go for the next one. Cycloalkane formed when 1,4-dibromo pentane is heated with sodium is A, methylcyclobutane, C, cyclopentane, C, cyclobutane, D, methylcyclopentane. So what is the this? So cycloalkane. So when you heat cycloalkane, so they have said which is the cycloalkane formed when 1,4-dibromobutane. So I'll write the structure of 1,4-dibromobutane. Okay. So this is dibromo CH2. So at 1, so this is 1, 2, then this is CH2, 3, this is CH3, 1,4-dibromobutane. Pentane. Okay, so 1,4-dibromopentane. So this will be CH3. So 1, 2, 3, 4, 5. So 1, 2, 3, 4. Okay, so it is 1,4-dibromopentane. When you have 1,4-dibromopentane, when it is heated with sodium, okay, when it is heated with sodium, what you get in the presence of dry ether? So it will yield what? So there will be elimination of what? There will be elimination of 2NaBr. Okay, so it will be 2NaBr. Okay, then you get your what? You get, so this will be the cyclopropane. Okay, so this ends will get joined. So this will be what? CH2, 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 CH2. Okay, so this will get joined and this will be CH3. So which is the cycloalkane obtained? It is methyl, right? So it is methyl cyclobutane. So 1, 2, 3, 4. So when you have 4 carbons, it is in a cyclic ring, it is called as cyclobutane. So it is methyl cyclobutane. So option A is the right answer. So which is the cycloalkane formed when 1,4-dibromopentane is heated. When 1,4-dibromopentane is heated with sodium. So I have written the structure for 1,4-dibromopentane. So structure is 1, 2, 3, 4. Okay. So when this gets, okay, so this will get eliminated with 2Na and this will get rejoined. Okay. So this is the, this is also example for a Wurtz reaction. Okay. So this is another reaction, that is a Wurtz reaction. So we'll go for the next question. I hope you have understood it. Yes. So when neo-pentyl bromide is subjected to Wurtz reaction, the product formed is, okay. So when neo-pentyl bromide is subjected to Wurtz reaction, the product formed is A, 2244 tetramethylhexane, B, 2244 tetramethylpentane, C, 2255 tetramethylhexane, and D, 2233 tetramethylhexane. So which is the product obtained when it is subjected to Wurtz reaction? So I'll write the structure of neo-pentyl bromide. So till you write the structure, you will not get a proper idea. So neo-pentyl, so this is neo-pentyl CH3, CH3, CH2, Br. So this is a neo-pentyl bromide is subjected to Wurtz reaction. Now you know for Wurtz reaction you require 2 molecules, right? So Wurtz reaction, so 2 alkyl halides. So plus 2 Na. Again, you will have Br here, then CH2, C, CH3, CH3. Okay, so this is a neo-pentyl bromide. So when neo-pentyl bromide is subjected to Wurtz reaction, what is the product obtained? Now you know what is the, this side product will be 2NaBr. Okay, so this is a side obtained, product obtained, that is NaCl. Now what you have to do? You have to join this. Okay, these two you have to join. So what will be the structure? Write it. CH3C, CH3, CH3, CH2. Then this will be CH2, C, CH3, CH3, and yes, write the structure now. Name. So this is 1, 2, 3, 4, 5, 6. So what is the name? Yes, what is the name? So it is 2. Okay, 2, 2, 2, 2. Then at 5, 5. Okay, you have 4. 1, 2, 3, 4. So when you have 4 means it is tetra. Okay, tetra. Which is a group? It is methyl. So 2, 2, 5, 5. Methyl. Tetramethyl. How many carbons are there? 1, 2, 3, 4, 5, and 6. Hexane. So it is 2, 2, 5, 5 tetramethyl hexane. Okay, so which is our correct answer? It is C. Okay, it is C. I hope you have got it. So whenever you have Wurtz reaction should be what? Wurtz reaction should be, you should have 2 molecules. Okay, you should have 2 molecules. So whenever you have 2 molecules, they should react. Okay, so they should react to give you a Wurtz reaction. So 2 molecules will react with each other in the presence of a metal like sodium. Okay, so this will be the product which is obtained. So this is Wood's reaction. I hope you have got it. Yes? Clear? Is it clear till here? So we can go for the next part. That is SN1 mechanism. We are going to start with nucleophilic substitution reactions. So we have already seen what are nucleophilic substitution reactions. So in this nucleophilic substitution reactions, we are going to see the two types, that is SN1 and SN2. That is substitution nucleophilic unimolecular and substitution nucleophilic bimolecular. Okay, so we'll start with the substitution reactions. Okay, so SN1 mechanism is called as substitution nucleophilic unimolecular. Why it is said to be unimolecular? Because the rate of the reaction depends on only one step and it follows first order kinetics. Okay, so this type of reaction, it proceeds in the following steps. So the rate of the reaction, it takes place with the two steps. Okay, the first step is a slow step. So first step is a slow step where there is a polarized bond. Okay, so you can see this is the tertiary butyl halide. You can see the first step. So I'll write first the reaction, how the general reaction. Okay, CH3 Br plus OH giving you KOH. I will write, giving you CH3 CH3 OH. Okay, so we are going to convert tertiary butyl halide into tertiary butyl alcohol. So the first reaction is a slow step reaction. So where there is a, you can see it will undergo a heterolytic cleavage. Okay, it will undergo a heterolytic cleavage wherein the carbon halide bond will be cleaved because there is a presence of electronegative atom. What it will do, there will be, so electron, as there is an electronegative atom, so it will tend to pull the electron towards itself. So as a result, there will be development of partial positive charge and partial negative charge. So when this bond breaks, the leaving group will leave with its pair of electrons and the carbon will have a positive charge. Okay, so tertiary butyl halide, what is happening here? There is a presence of halogen atom. So what it will happen? So halogen atom, it will tend to pull the electrons towards itself. As a result, there will be development of partial positive charge and partial negative charge. Okay, so partial negative charge on the halide group and partial positive charge on the carbon group. So as a result, when the leaving group will be leave, it will take the electron, pair of electron with it, and it will leave. Okay, so and the carbon will have a positive charge. So and it will form what? It will form a carbocation. So this is a carbocation which is formed in the first step. So first step is the formation of carbocation. So first step is what? First step is a slow step and it is called as the formation of carbocation. So in the first step, it leads to the formation of carbocation. Okay, so we'll see the second step now. So we are going to convert the alkyl halide into what? Into alcohol. So second step, what will happen? It is a very fast step where the nucleophile, that is here nucleophile we have taken is OH minus. So this OH minus will attack the carbocation. Okay, it will attack very fast. This is a fast reaction and it will form a tertiary butyl alcohol. You know that carbocations are unstable. Okay, carbocations are unstable. So the nucleophile which is present, nucleophile, what it will do? Nucleophile will attack the carbocation. Okay, nucleophile will attack the carbocation and it will form what? It will form a tertiary butyl alcohol. So the first step, as I said, it is a slow step and it is a rate determining step. So the first step is very slow step and it is a rate determining step. So the rate of the reaction, so the rate, so the first step is a slow step and it is a rate determining step. The rate of the reaction depends on the concentration of only substrate. Okay, the rate of the reaction depends upon the concentration of substrate. Now, what is substrate here? What is substrate? This is the substrate. So rate of the reaction depends upon the first step, right? So this is the substrate. So rate of the reaction depends upon this substrate. So this is called as the substrate. This is CH3, not CH2. This is CH3. Okay. So rate of the reaction depends upon the substrate. The first step is a slow step and it is a rate determining step. So rate of the reaction depends upon the concentration of substrate. So it follows the first order kinetics. Then when we are seeing the order of reactivity, so when we are seeing the order of reactivity of alkyl halides, so the order of reactivity depends upon the stability of carbocation, which is formed in the first step. So in the first step, we know that it is a slow step and there leads to the formation of carbocation. So whenever the carbocations are formed, so tertiary carbocation is more stable than secondary carbocation and then the primary carbocation. Okay. So it may also be noted that when you have an optically active alkyl halide, SN1 reaction will result into racemic mixture. Now, what do you mean by racemic mixture? Racemic mixture means you have 50% retention and 50% inversion. Okay, 50% retention and 50% inversion. Now, what do you mean by retention? Retention means what? Suppose I have this reaction CH3, 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 Br plus KOH giving you C, CH3, 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 OH. Now what is happening in this reaction? Yes, only the Br is replaced by OH and here, right? So rest all molecule is the same. Right, rest all molecule is the same. Only the Br has been exchanged with OH. So such, okay, so the configuration wherein it is similar, okay, in the configuration where there is no change in any optically active compounds, if there is no change in configuration, then it is called as retention. Now, what do you mean by inversion? Okay, what is racemic mixture? I said, so racemic mixture is you have 50% retention, okay, and 50% inversion. You have 50% retention, 50% inversion. Now, what did I say about retention? When you have the other molecule is similar, only there is change in this leaving group. So Br has been replaced with OH group. Rest all molecule will be same. Then it is called as retention. Now, what is inversion? What is inversion? So suppose CH Br plus KOH yes. Now you can see the difference. What is happening here now? In this case, you can see this is a CBr group. Okay, here it is CBr and here it is COH group. Right. Is there any change in configuration? Yes, there is complete inversion, inverted. Right. The molecule is inverted. So it is called as inversion. So what is happening here? The OH group is attacking from the behind. Okay. So as the OH group is attacking from the behind, this will leave and this will form like this. So this is called as inversion. So when you have 50% inversion and 50% conversion, inversion and 50% retention, then it is called as what? Then it is called as racemic mixture. So this is racemic mixture. So what is first order kinetics? First order kinetics, it depends upon the rate of only concentration of substrate. Okay. So this the first step is very slow step and it is called as rate determining step. Then stability of carbocation depends upon the reactivity of the carbocations. Okay, it depends on the carbocation. That is tertiary is more stable than secondary and then the primary. Okay, so this is about the reactivity order. So this is about SN1 mechanism. Then we are going to see about SN2 mechanism. So what do you mean by SN2 mechanism? SN2 is substitution nucleophilic second order. Okay, that is bimolecular. It is called what? It is called as bimolecular. Okay, substitution nucleophilic Substitution, nucleophilic, bimolecular. Bimolecular means what now? The rate of the reaction depends upon the concentration of so SN2 reaction, substitution, nucleophilic, second order. Okay, so bimolecular reaction, this type of reaction occurs in one step. Okay, so rate of the reaction depends upon the concentration of only one step. So here you can see, so here they have taken a methyl halide. Okay, you have taken a methyl halide. So here the leaving group will, the nucleophile, that is OH group, will attack from what? It will attack from the behind. Okay, it will attack from backside, OH group. So this is OH group. Okay, so OH group will attack from the backside, and what will go? It will undergo a transition state. So transition state is such a state where it will have a pentavalency. It will have a pentavalency. What do you mean by pentavalency? More than 5 hands. Now carbon, it will have only tetravalency. So it can form only 4 bonds. Okay, but here it is having pentavalency, which is unstable. It is unstable. So carbon, what is happening? Carbon, so the leaving group, okay, this is a leaving group and this is an incoming nucleophile. So the incoming nucleophile will make the bond and the leaving group will break the bond. So making of the bond and breaking of the bond takes place simultaneously and it undergoes a transition state. So the leaving group will leave and it will form a inverted product. Okay, so this will form what? Alkyl halides are converted into methyl alcohol. So here what happens? Here the nucleophile will attack from the opposite side of that containing the halogen atom. So the rate of the reaction will be directly proportional to the concentration of the substrate as well as the nucleophile. So here the rate of the reaction depends on 2 factors. One is the substrate, another is the nucleophile. So it is called as bimolecular reaction. It is a bimolecular reaction, but it will undergo by a one step. So it is a one-step reaction. And the SN1 reaction will what? SN1 reaction is unimolecular reaction. It is a unimolecular reaction, but it is a 2-step reaction. It is what? It is a 2-step reaction. So here in SN2 reaction, the rate of the reaction depends on the concentration of nucleophile as well as the substrate. Okay. So the order of reactivity of alkyl halide is, so what will be the order of reactivity as we seen? So here the order of reactivity of alkyl halide is primary carbocation is more stable, then secondary, and then the tertiary. So why your tertiary is not stable? Suppose if I take a tertiary alkyl halide here, okay. Suppose I take a tertiary alkyl halide, so C. So I've taken a tertiary alkyl halide. Okay, so this is a tertiary alkyl. Just what I've done, I have written the complete structure. So I've just elaborated the CH3 groups. Now here in this case, and I've taken a primary alcohol. Okay, I'll take a primary alkyl halide. Now what is happening when you take a tertiary alkyl halide? Now in what is SN2 reaction? In SN2 reaction, the rate of the nucleophile attack will take place from behind. Now here when you want to attack the nucleophile from the behind, you can see that the molecules are larger. Right, there are huge molecules, or you can say there are large molecules. So attack of this nucleophile on this carbon will be very difficult. What is the reason? It is due to steric hindrance. Okay, so what is the reason? It is due to steric hindrance. So there is large, so CH3 groups are bulkier groups. So because of this, the nucleophile cannot attack this carbon. Okay, it cannot attack this carbon from backside. So as the CH3 groups in case of tertiary alkyl halide, it is bulkier. CH3 groups are bulkier groups. So because of this reason, what is happening? The attack will not take place, and thus carbocation formation, the tertiary will be unstable. Okay, and that when you compare it with the primary, okay, if you take a primary alkyl halide, so what will happen here? So easily the OH can attack from behind. Okay, there is no steric hindrance. Okay, so there is no steric hindrance, so easily the OH can attack. So tertiary carbocation, so the stability of this is primary will be more stable than secondary and then the tertiary. So it is noted that in case of optically active alkyl halides, SN2 reactions are accompanied by inversion of configuration. So as we have discussed in SN1 reaction, it will undergo racemic mixture or racemization. That is, it will show 50% retention and 50% inversion. But in case of SN2 mechanism, it will show 100% inversion. Okay, the molecule will get inverted. So it will show inversion of configuration. It is also called as Walden inversion. So this SN2 mechanism, it is also called as, it will show Walden inversion. So we'll solve some MCQs based on this. So the order of reactivities of the following alkyl halides for a SN2 reaction is. So what is the order of reactivity for the following alkyl halides for a SN2 reaction? So these are the options. A, RF is greater than RCl is greater than RBr is greater than Ri. Then B, RF is greater than RBr is greater than RCl is greater than Ri. Then C, RCl. Okay, so these are all are alkyl halides. So RCl is greater than RBr is greater than RF is greater than Ri. And D option, Ri is greater than RBr is greater than RCl is greater than RF. So which of the following order of reactivities of alkyl halides for SN2 reaction? What will be the order of reactivities? Okay. The answer is D. Okay. The answer is D. So we know that as we go down the group. Okay. So how is the halogen? So group 17, chlorine, fluorine, bromine, and iodine. As you go down the group, what will happen to the size? The size will go on increasing. Right? The size will go on increasing. Right? So with the increase in the size of halogens, okay, the CX bond energy, what will happen? It will also increase, right? As you go down the group, as the size increases, what will happen to the bond energy? Bond energy also will increase, right? So therefore, the reactivity of alkyl halide will decrease, okay? So option D. So Ri will be greater than Rbi is greater than RCl and Rf. So the order of reactivity in case of SN2 mechanism will be D option. I hope it is understood. So as you go, okay, with the decrease in the size of halogen, as you decrease the size of the halogen, the CF bond, okay, energy also increases and therefore reactivity of alkyl halides will decrease. So this is the reason. So we'll go for the next question. Tertiary alkyl halides are practically inert to substitution by SN2 mechanism because of A, insolubility, B, instability, C, inductive effect, D, steric hindrance. Why tertiary alkyl halides are practically inert to substitution by SN2 mechanism? Just now we have discussed about it. Why tertiary alkyl halides cannot undergo SN2 mechanism? Yes. Yes, so it is due to steric hindrance. So just now we have discussed it. So when you have a tertiary alkyl halide, so due to bulkier groups, okay, due to bulkier groups, what will happen? So due to bulkier group, what will happen? So the attack of the nucleophile will be difficult. So because of this reason, that is, it is due to steric hindrance. Okay, so it will be restricted. The attack will be restricted. So which of the following is correct order of decreasing SN2 reactivity? So which of the following is the correct? Which of the following is the correct order of decreasing SN2 reactivity? Okay, Archana has messaged that A. Aishwarya has answered it as B. Komal has answered it as A. So here, so which of the following order is the correct order of decreasing SN2 reactivity? It is A. Okay. So in SN2 order, you know that primary is more stable than secondary and then the tertiary. Okay. So order of reactivity. So this will be primary, then the secondary, and this is tertiary. So the correct order of decreasing reactivity will be this. So we'll go for the next question. The organic chloro compound which shows complete stereochemical inversion during a SN2 reaction is. So which is the organic chloro compound which shows complete stereochemical inversion during a SN2 reaction? Yes. Okay. So whenever you have a for SN2 mechanism, you know that primary will be more stable than secondary and then the tertiary alkyl halide. So here you have to see which is primary, which is secondary and tertiary. So here A option, it is primary alkyl halide. So primary alkyl halides, it will undergo easily complete it is first one. So A option is the right answer. So we'll go for the next question. A solution of my 1-chloro 1-phenyl ethane in toluene racemises slowly in presence of a small amount of SbCl3 due to the formation of A free radical, B carbanion, C carbene, and D carbocation. Okay, I got the answers as D. Okay, so 25th, it is D. Okay, so answer is D. So you know that. So 1-chloro 1-phenyl ethane in toluene, it racemizes slowly in presence of small amount of due to formation of carbocation. Yes, so answer D is the correct answer. Okay. Which one of the following is not true for the hydrolysis of tertiary butyl? Which of the following is not true for the hydrolysis of tertiary butyl bromide with aqueous NaOH? A. Reaction occurs through the SN1 reaction mechanism. B. The intermediate formed is a carbocation. C. Rate of the reaction doubles when the concentration of alkali is doubled. D. Rate of the reaction doubles when the concentration of tertiary butyl bromide is doubled. Reaction. So when you have tertiary butyl bromide is what? Tertiary butyl bromide. So this is tertiary butyl bromide. So tertiary butyl bromide, it occurs what? The reaction will undergo. So when you have a tertiary alkyl halide, it will undergo SN1 reaction. So this is a true statement. The intermediate formed is carbocation. Yes. So the carbocation is only formed. This is also correct. Then C option is what? Rate of the reaction doubles when the concentration of alkali is doubled. Rate of the reaction doubles when the concentration of tertiary bromide is doubled. Okay. So the rate of the reaction depends on what? The rate of the reaction depends on the concentration of substrate. So this is the correct answer. It does not depend upon the concentration of nucleophiles. So this is wrong. So this is the answer. Okay. So C is the correct answer. So C is the correct answer because which of the following they have asked which is not true. Okay. So rate of the reaction of in SN1 reaction depends upon the concentration of the substrate and not on the nucleophile. So if you double the rate of the reaction, with respect to concentration, then the rate of the reaction also will double. If you increase the concentration of alkali, okay, so this will not impact the rate of the reaction because it does not depend upon the rate of the alkali. So it depends only upon the concentration of substrate. So this is a wrong statement. C will be the answer. Okay, so today we have discussed. Okay, so today we have discussed some of the questions based on elimination reaction, right? Then we had started with the substitution reaction, right? So we have started with substitution reaction. We have seen SN1, SN2 mechanism. Then we have solved some MCQs based on substitution reactions. Okay. So I hope it is clear. Okay. So in the next session, we'll be starting with the optical activity. So I'll end the class here. Okay.